Hi ladies and gentlemen, in this short video let me explain the delta modulation. It's a small variation in the DPCM system. So, so in this first we will see the learning outcomes, then the delta modulation system, and then the summary of understanding. Of course, I will tell you something about the signaling codes also. So here you will learn the block diagram of a delta modulator and demodulator. Then you will learn the time slope overload and granular noise. Then you will learn the condition for avoiding slope overload, and we will briefly discuss the signaling codes for transmission. So it's, delta modulation is nothing but a small variation in the DPCM system we have seen. In this, the cornerstone of a differential PCM system is a linear predictor. So that is nothing but an FIR filter. If that FIR filter has only one delay element, it becomes a delta modulator. That is just one delay element. Then it becomes a delta modulator. So usually in the case of a delta modulator, the input is oversampled. Means the sampling rate is much greater than twice the modulating signal, twice that of the modulating signal. The sampling frequency is much greater than 2 FM. So that increases correlation between adjacent samples. So what we do is you take the difference between the input and the approximation, which is nothing but a delayed version of my input. If that is positive, you decrease the step by 1. If it is negative, you increase the step by 1. So this delta modulator actually provides a staircase approximation of the sampled signal. So this is a system. This is just like our earlier DPCM system, except that this instead of a predictor here, I have only a delay element, just one delay element here, one Z inverse. So this gives here the speech signal is coming. Mn is my speech sample. This mqn minus 1 is the previous value of the quantized speech signal. So it takes a difference between this mn minus mqn minus 1. So that gives me an error signal en. And here, in contrast with the DPCM system where I use a logarithmic quantizer, here in the case of delta modulation, I use a binary quantizer. So this binary quantizer, what it does is, if this En is positive, this will reduce the step by 1 delta. If it is negative, then I will have plus delta. Okay. So this gives me a quantized value of En, though this quantized value is added with previous value of my quantized signal to form the input to the predictor, which is nothing but a delay element here. So this is my mq and my n, and this is mq n minus 1. This eq n minus 1, this is either plus or minus delta, that is encoded and sent out as binary signal. So this is how the modulator, the delta modulator works. And here you can see that you can see this demonstration. This is my speech signal empty. So this steps are going like this. Here this step is below empty. So what happens is my quantizer advances the step by 1 delta, so that it is above that. It stays this way for 1 TS. This is one sampling interval. Then here you can see that the step is above the speech signal, so the step is depressed by 1 delta. It comes here, it increases here, it increases this way. So likewise this follows a staircase signal. So as far as the demodulator is concerned, it is very similar to our DPCM system, except that the predictor is replaced by Z inverse. So I have the received signal coming here. I have a decoder, a binary decoder here. Here this forms a kind of an accumulator system, and then followed by a low pass filter. So this accumulator together with this decoder and low pass filter, that makes a delta demodulator. Now one problem that can happen in delta modulation is called slope overload. If the slope of the input signal is fairly large, see here the slope of this empty, the message signal is very large. So what happens is here the step is below this, so it comes here, it barely touches here. It comes here, it comes here. It takes some time to catch up with the signal empty. This is called a slope overload. So this is because the slope of these steps are smaller than the slope of my message signal. So I can encounter another problem if if the input is remaining in this way flat for some time. What happens is these steps oscillate around this signal value. So that results in something called a granular noise. So if the input slope is small, then the steps alternate around a feeble input signal, so causing something called a granular noise. But you can overcome the slope overload error by proper choosing of this delta. That is, in order to not have any slope overload, the slope of the step should be greater than the slope of the input signal. So that means delta by ts, this is the slope of the thing, because delta is my y-axis distance and ts is my sampling interval. So delta by ts is a slope of the steps. So that should be greater than or equal to absolute value of the slope of mt, which is dmt by dt. So this is one condition in which you can, so delta should be greater than or equal to ts into modulus value of dmt by dt. By properly choosing this delta, you can reduce the slope overload. And when I come to the actual transmission, this is somewhat different from my source coding scheme. With the source coding, you can generate binary signals, but there is a question how I can transmit these binary signals over a wire or a communication medium. So these are all baseband transmission, that is without any digital modulation. How can I transmit a binary data over a wire or a communication medium? So for that I use some kind of signaling codes. So what we have seen in the first part, that is called source coding, that those methods called PCM, delta modulator, or DPCM, they are all source codes. What they do is they convert a source symbol into a binary code. Now these binary codes have to be transmitted over a communication medium using baseband transmission. So for that I use some other codes, that is called a signaling codes. Okay. So one popular signaling code that here is this called a unipolar non-return to zero coding. Okay, unipolar non-return to zero coding. So what it says by unipolar is that it stays positive or negative. Say here it is unipolar because it is plus v, there is no minus v, plus v and zero. This is unipolar in nature, not bipolar. Non-return to zero means this is my TS duration, this is my data interval. During this data interval, it does not come back to zero. So it does not return to zero during this TS period. So during this TS period, I have during this during this bit period, not the sampling period, but the bit period, I have this doesn't go back to zero. So this is a 1, so I have a plus v here, there's a 0, then a v, okay, so 1 1, then again a 0, 0 0 0. So this is a unipolar non-return to zero signaling code. This is a bipolar non-return to zero signaling code, means 1 is represented by a plus v and 0 is represented by a minus v, then plus v, then minus v, minus v, minus v, because these three are zeros. So this is a bipolar non-return to zero. Now when I think about a unipolar return to zero code, this is unipolar in nature, but this is a 1, but this doesn't remain at 1 for all the bit duration. Instead, half of it comes here, a short pulse. Okay, this is the full bit period. It stays high for a certain time only. Okay, so this is unipolar return to zero. During this interval, it returns to zero, stays here. This is a 0, it remains at 0. Here it's again a 1, so it goes high, it comes back to 0, returns to 0 here. Then comes here, again goes high and return to 0 here, and remains at 0 because these are 3 zeros. Then again it goes to 1 and returns to 0. And bipolar return to 0 means this signal will be bipolar in shape. That is, here it is a 1, so it is plus v. It returns to 0 at the middle. It stays at 0. Then you see a 0, so it goes to minus v. Okay, it returns to 0 here and stays at 0. Then it sees a 1, so it goes to plus v and returns to 0. Here again plus v, returns to 0 here, that way. Now that is a bipolar return to 0 code. Then there is another code called alternate mark inversion code. Alternate mark inversion code. So what that does is first one, that is a return. This is a return to 0 code. So this remains at high, and 0 it remains at 0. For the next one, the polarity is reversed. Okay. first for the first one it has a positive polarity, then it came back to 0, it returned to 0. It's a return to 0 code. So during the 0 it stays at 0, then it sees a 1. So that one I have there's a mark inversion, there's a polarity inversion for that one. Then it goes back to 0, it comes here again, it sees a 1. So again there is a polarity inversion, it's a plus V here. Then it stays at 0 because I have 3 zeros again. Then when the next one comes, the polarity is again inverted. So that is called a alternate mark inversion code. That is another signaling code. Then the last code is a Manchester code. Here in the Manchester code, a 1 is represented by a high to low transition and a 0 is represented by a low to high transition. So what happens is it sees a 1 here. So at the middle of this, it makes a high to low transition. So this high to low transition indicates that this is a 1. It stays at low and then it sees a 0. So here it makes a low to high transition. This low to high transition is a 0. Then it remains at high. Again it sees a 0. Sorry, it sees a 1. So it makes a high to low transition here. Okay. Then here again it's a high to low transition. Okay. Then here it's a 0, so it makes a low to high transition. Okay, this is a low to high transition, this is a low to high transition because I have 3 zeros here. Then here comes a 1 comes, it makes a high to low transition. That's called a Manchester encoding. So in your syllabus it is concerningly mentioned, other details are not there. So you understood the block diagram of delta modulator and demodulator. Then you learned the terms slope overload and granular noise. Then you understood the condition for avoiding slope overload. Then you understood the signaling codes. And that is the end of this presentation. I thank you all.